Let's start with how can we improve the generative model. This is a joint work with Microsoft Research and University of Texas at Austin, which got accepted recently in CVPR. From a generative model, we might have two expectations. One expectation is when we have some samples of data, how can we estimate the density that this data is generated from? The other expectation that we might have is when we have some samples from the data, how can we generate more samples from that data distribution? Which in here, the data distribution, the samples are, each sample is one image. And these samples has not been seen during training of the generative model. In this talk, we mainly concentrate on the sample generation quality of the generative models. But why having more samples is something useful? Before we explain how we actually improve them. So I put here several examples that shows the importance of more sample generation. One of the reasons is we can actually make a virtual reality. The other main important thing is we can train a robot in a virtual reality environment rather than a true environment. That can be very crucial and important because, for example, if we want to train a robot to go through the people and do some delivery, one way that robot can be trained is we put it actually in the real environment and it goes through the people, but it's so costly, both in terms of the time and in terms of maybe that robot hits something and it needs to be fixed and it needs to be fixed, which is costly. But in a virtual reality environment, it can be done much more faster, and it can. The cost of that iteration is probably so much lower. The other thing that we can do is if we have some scratch of the images, we can actually make the real images, and that can be used for photo editing, searching for images, and so many other applications. The other use of our generative models are when we have missing data. For example, let's say that we have low resolution image and we want to make a high resolution image. And generative models has been shown that they can produce a real high quality data. And the other example of using the generative model is something like this, that we write a description and it provides for us some images. For example, in here, we wrote a description of a baby, very cool radish in the tattoo walking the dog, and it prompts some images that didn't exist in our training set before. Now that we have seen some application of generative models and why they are important, let's explain GANs. GANs are essentially one of the most successful generative models in the machine learning community. I think most of you are probably familiar with this topic, so I just try to explain very briefly what is GAN. So GAN consists of two neural networks, one called generator and the other one called the discriminator, which essentially the generator acts like a counterpart and the discriminator looks like a cop. That the generator tries to generate some samples of a data, and if a data is image or painting, each time the generator generates some painting, and the discriminator, which is here is a cop, is responsible to guide the generator to become better and better by rejecting the low quality painting that person present, which they iteratively improve each other until the counterpart could generate a high quality image. So the whole thing can be perceived as a generator, as a counterpart, and discriminator as a as a cup, which they get which the discriminator gets samples of real images and fake images and try to distinguish them correctly with the related loss function. And the generator tries to fool a discriminator with the oppositely directed loss function. And by optimizing these two loss functions for the discriminator and generator, then we train a generative model. But GANs, although they have been successful in the literature, it's still known that they have some shortcomings. So one of the main shortcomings that they have is mode collapse. In here, I'm gonna use a simple 2D toy data example to provide this illustration about their shortcoming. So let's say that our real data distribution is a mixture of 25 normal distributions in this grid. And we feed this data to a generative model, to the GAN, and we try to estimate the whole density using these samples. So usually GANs estimate something like this, which is not ideal because, as you can see, some of the modes are missing in the generative model, that refers to the mode collapse in the literature. The other problem that they have is they put some unrelated data in something between two modes, which is not desirable and which is a wrong estimation of true data density. So our main idea to address the two mentioned challenges with the generative model is to first partition the space, train a different generator or GAN on each region, and guide each generator to only generate sample from its region. For example, let's consider that this manifold is for a manifold of images related to the cat, and this manifold is related to the dog, and this manifold related to airplanes. So we want to have a different generative model for each part of the data to not miss any of these modes. And we don't want to generate something between these two modes, something between cat and airplane, because it's not something realistic. But let's start with each component. So the first component was how to partition the space. So to avoid mode connecting, let's simplify the problem. Let's say our data is like a spiral. It's a three-spiral component. So if you want to partition this data to three components, one way that we can partition is in this way, that put the red dots in one component, green dot in one component, and blue in another. But this is not a good way of partitioning because still within each component we have disconnected manifolds. So then we generate something between these components if we want to have a single generator to generate from this data. So an ideal way of partitioning is we put disconnected manifolds in a different partition of the space. Our partitioning method consists of three main parts: learning useful representation, make a k-nearest neighbor graph, and put the connected nodes in the same partition as much as possible. So for learning a representation, we want to, let's say we have a set of images, and some of our dog and some of our cat and some of our airplanes. So we want to learn a vector representation for each image that images of the same class be closer to each other rather than images from different classes. So after we made that representation, I show it here as different nodes. We make a k-nearest neighbor graph on top of those representation. And afterward, we put connected nodes in the same partition as much as possible. Then we do the partitioning or clustering of the space. Let's start with how should we learn the representation. In this slide, I explain how we train a neural network that change one image to a representation. So let's say we have two images. One is images of a dog, and the other one is an image of a chain. So the main idea is if we randomly crop and change the color of the image and make two versions of them, and for example, one for the dog and one for the chain. And if we pass these four images through a neural network, then we expect the representation that we learn for the noisy version of one image to be closer to each other than representation of two images that are not from the same initial photo. This has shown a huge success recently in computer vision. And after we learn the representation, we make a k-inverse neighbor graph in that space of representation, and we put the nodes or images that are close to each other in the same partition as much as possible. And this is the objective function that we have to train the neural network. Okay. So now that we are done with how we do the partitioning of the space, let's discuss what are the challenges for training different GANs on each region of the data. So training a different generator on each part of the data has two main challenges. Is first, if we want to train one GAN for each part of the data, then we have so much less data to train that generator, which is not efficient. We are usually in the regime of low limited data samples. The other challenge that we have if we want to train different generative models, because each generative model has so many parameters. So if we want to have hundreds of generative models, then we need to have 100 times more computational complexity, which is essentially not feasible. To alleviate the two aforementioned problems, we propose weight sharing between different generators and discriminators that then we don't need to have so many parameters to train. And essentially, for our case, our generator only are different in the first layer, and the discriminator only are different in the last layer. So this drastically decreases the number of parameters. This also helps us to use data efficiently across different partitions, because essentially each generator can see the data from the other region too. So now that we are done with training the different generator and their challenges, let's see how can we actually guide each generator to generate sample from only that region. To guide to each generator to only generate sample from its region, we actually need to define a concept of a distance that when a generator generates a sample far from the partition that is designed to generate sample from, we need to say how much this sample is far from this partition of the space. So we need to have a distance, the concept of the distance. And in here, we define the concept of distance based on our differentiable space partitioner logits. Then after we have this concept of the distance, we can parallelize each generator samples or a generator if it's far from the area that is designed to generate sample from. And this is and the other term is related to the generative adversarial network criteria. But we realized that this simple trick may not work because we need to take into account some consideration and about the architecture of the space partitioner. And we first theoretically developed what should we have done for the architecture, what criteria need the architecture needs to have. Then we design a neural network architecture that satisfy that criteria, which we showed here. So the previous architecture, as you can see from here, for a partition of data in the corner, uh, it wasn't ideal because as we go further from this partition of the space, the distance sometimes has some, and the negative distance has some local optima, which shouldn't be the case. But the new change of architecture made it so desirable that when we get further from this partition, the negative distance also decreases. Here are some samples of our generative model. None of these images that you see right here are in our training set, and we just generated them using the generative model. And in here, I put the plots, I put the images for the lower resolution training data. It's actually 48 by 48 resolution rather than this one, which is 128 by 128. And as you can see, we did a good job in first separating different data to different categories. So we put the airplanes in one category and the car in the car category, and we didn't have the labels during training time. And the other thing that you can see is for a real data, we could generate some acceptable synthetic data that looks like real images, although they don't exist in the real data images. To capture the goodness of a generative model, actually two metrics exist. One is FID and one is inception score. FID lower is better, inception score the higher is better. And we drastically improved the FID and inception score 25 to 19 and 9 to 11 for the STL10, which dataset, and also for ImageNet dataset, which is actually very large. It has 1.2 million images. We also drastically improved the FID from 40 to 21 and from 15 to 23 on unsupervised image generation. And at the time that we published this paper, we were the state of the art in unsupervised image generation when augmentation techniques has not been implemented.